Suppose you're on a ice hockey rink and you hit the puck straight down the rink, okay? And but there's a problem. Whoever finished the hockey rink made it slightly biased to this direction. Or in other words, if I were looking from behind the puck, there's a slight incline to one side. So if this is the puck traveling away from me, there's a slight acceleration due to gravity down in this direction. Okay, so this would be a top view up here, and this would be a back view down here. So that would mean that there's an acceleration that's going this way. Okay, for this path. And so the question is, after a certain time, where would this puck be? And more so, how does it get there? Okay, so let's think qualitatively for a second what the path of this is going to be. So initially we have a very perpendicular acceleration. The acceleration is this way, and the velocity is this way. I'll go ahead and put a v here to indicate that velocity, which means that this is mostly going to be changing the direction of this. It's going to do very little to speed it up. And so at a later time, it's going to be angled downward a little bit. And at a later time, it's going to be angled downward more and start speeding up because now there's a component parallel to this acceleration. So we see that as it's wanting to travel this way, it's going to also start traveling this way and more. And so hopefully, and we will, see that the equations, the kinematic equations, will show this parabolic motion. It curves more and more strongly in the direction of the acceleration. Okay, so at some later time, that puck's going to be right there. Okay, so to solve this problem, we're going to need to be very careful to write everything in terms of components. So first off, let's define a coordinate system. Now we have two coordinates of importance here. We have a coordinate this direction. I'll call it the x direction, so that would be the initial direction of motion, the motion down the rink. But I'm going to also include a coordinate this way to the right of the motion of this, or down the page in my picture, that indicates this direction of this acceleration. I'm going to call that y. And note that's not a conventional coordinate system, which is okay. I'm choosing this y to be pointed in the direction of the acceleration so that my velocities will be positive, as well as this acceleration. It just makes it a little bit easier, but that's the power of the coordinate system. You can choose your coordinate system to make your problem easier to understand, but you just need to be consistent with it. I could have chosen y to be this way, and then I would end up with negative velocities and negative acceleration. Okay, now that I have my coordinate system established, what are all the kinematic variables right here? So just like before, I've got a t0, and I have an x0 and a y0. I also have a v0x and a v0y. I've got 5 kinematic values for that one location. This may seem really tedious to write that all out, but it's reminding me of the difference between these velocities and these positions. Okay, it's very common, without being particular about this process of writing out all possible variables, to confuse them and get them mixed up between them. Alright, so similar down here, I've got my acceleration. Well, let me do my acceleration first. So my acceleration, I'm going to go ahead and write, it can have an ax and an ay. Okay, but this case I have found it really valuable right away to cross off one that's any that are 0. In this case, we don't have any ax. Okay, now I could have done that up here too. I haven't found that to be as big of a deal, but I have found students will forget to recognize that ax in this case is 0, and they'll plug in a value that is non-zero when they start plugging it in. So I found it really good to right away say, okay, does my acceleration have components? Is it one-dimensional? Is it one-directional? Then show that right away. Okay, and we'll get these other pieces as we come. You don't have to do that, but I found it to be very helpful. Okay, now down here, this one's moving. It's at a later time, t1, an x1, a y1, a v1x, and a v1y. So again, 5 kinematic variables for this two-dimensional situation. What do we know? Okay. Alright, I can always start my time so that t0 equals 0. I've chosen my coordinates so that x0 and y0 are both 0. My v0x is whatever this velocity is, and I'm just going to call that v0. Okay, so v0x is just some value of v0. Alright, my v0y is 0, because initially, at the very moment I begin, it's moving only in the horizontal. So v0, or only in this direction. So v0y equals 0. Alright, now, what do I know? What else do I know? I know, I'm going to go ahead and show it again. I know that ax equals 0. And that's the important one here. Ay, I'll just say it equals a. We could figure that out from a different problem. We know this is effectively an incline, but I want to focus just on the two-dimensional part here. Okay, T1, my question is at a later time, where is it at? And so T1 is the time of interest, and I'll just call that just some random T. Okay, that we can then plug in different values for that. So I can say at 3 seconds or at 10 seconds. I could have left it just as T1 also. Alright, but it's a known. I know that. And I don't know x1, I don't know y1, I'm looking for those. I don't know v1x, and I don't know v1y. I'm not looking for those. I could have, but I don't know those, and in this problem I'm not looking for those. So finally I can put find, and I've got x1 and y1. Okay, so now I'm ready to try and solve this problem. Okay, so give me some organizational space here. Let's consider finding x1. Okay, now ax is 0 is really nice. I know my times, and I know my initial position and my initial velocity. So that suggests, but I don't know my final velocity. So that suggests I use this equation. x1 equals x0 plus v0x times the time interval, delta t, plus 1/2 ax delta t squared. I write out the whole thing, even though I know x is 0, because, and it happens way too often, the students will forget, and they'll put in a non-zero value for this ax. But by writing the whole thing out and say, okay, what is ax? Oh, it's 0. I can cross that out correctly. This one is 0 because of my coordinate system, and this delta t is t minus 0, so it's just going to be t. So I can say that x1 is equal to v0x times the time. And now, if I give you, oh sorry, just v0, because v0x is v0 times the time. So now I give you a value of v and I give you a value of t. You can tell me where it is down the rink, you know, how far it's traveled this way. Okay, so we have that one. Similarly for y, y1 is equal to y0 plus v0y delta t plus 1/2 ay delta t squared. Okay. Now in this case, ay is not 0. It's some value, some constant value a. But v0y is 0. It's only moving initially in the direction down the rink. So v0y is 0. y0 by my coordinate system is 0. So I end up with y1 equals 1/2 a. ay is just a. And then delta t is t minus 0, so just t, at squared. Okay. So now I can find those individual values if I was given known values for initial velocity and the acceleration to the side, and any time later. Now what's interesting here is the motion is very separate. They're distinct from each other. So the horizontal motion continues on at that same velocity and just keeps doing it. Okay, the final position is just the velocity times the time, or I could rewrite that and say velocity is equal to the position divided by the time, which is constant. So the velocity just keeps on going. So there's no difference here. The position in the y direction, or to the side of towards the side of the rink, is changing with time squared, which means its velocity must be changing. So that's how we get parabolic motion, is it continues linearly this way, but continues as a square this way. So as time ticks on linearly this way, the y position changes as the square. So we were able to now use these separate components to find that.